Wonderful. So Nima has set the stage about the physics from the very small to the very large, and I'm sure you'll have questions, and we'll take them soon. But now we'll have Ashoke tell you about the enterprise of string theory in a little bit more detail, and how it impinges on the questions that Nima brought up. So let me just tell you a little bit about Ashoke. I guess you've all heard of Ashoke, and in a way I don't know where to start in trying to introduce him. I myself have had the privilege of being a colleague and a neighbor of his at the Harish Chandra Research Institute for the last dozen or more years, and it's really been privilege knowing him and seeing him at such close quarters. Ashoke is one of the most remarkable theoretical physicists of the world today, and I think he's truly one of the gems of our country. I mean, I know he'll be embarrassed by this, but I think it's really something we can all be truly proud of, and without any reservations in our country. His pioneering work on dualities changed the face of string theory, and his deep insights into black holes in string theory have made us all so much more confident about the enterprise of string theory. I could go on and on, but anyway, I won't keep you waiting for his talk. I just wanted to say that he has all the various scientific honors of the country, but he's also the only Indian working in India who's been awarded the Dirac Medal, the prestigious award from the ICTP. This is something he received last year. And he's also one of the recipients of the inaugural Fundamental Physics Prize, like Nima. So we're very lucky to have both of them here today. And so without any further delay, let me invite Ashoke.
Okay, it's a great honor for me to be here giving this talk. And so what I plan to do today is to tell you something about string theory. Okay, so the question that I'll try to address in this talk is, what is string theory? I'll give a very brief introduction. Okay. So before I get into any more details, let me just give the answer in a few words. Okay. So string theory is an attempt to find a unified theory of the elementary constituents of matter and the forces that operate between them. And this involves study of the laws of the universe at small scales of the order of 10 to the minus 33 centimeter, which goes far beyond our familiar scales, the sizes of atoms and nuclei. Okay. So before I discuss string theory, I have to give a history of why string theory came into prominence. So I begin with the modern understanding of the ultimate constituents of matter, and I am sure most of you are familiar with most of this diagram. So at the crudest level, we can think of the molecules as the basic building blocks of matter. Okay. But we know that the molecules are made of atoms. Okay. Each atom in turn is made of a central nucleus and a cloud of electrons around the nucleus. Okay. We also know the nucleus, each nucleus is made of a bunch of protons and neutrons. And finally, protons and neutrons themselves are not elementary particles, they are made of quarks and gluons. Okay. These are, as far as we know today, truly elementary. Okay. So quarks, gluons and electrons. Okay. But at the same time, I should add that these are not the only elementary particles we know of today. In fact, these particles are a small subset of a whole zoo of elementary particles, okay, some of which you saw in the earlier talk given by Nima. We also have very good understanding of what kind of forces operate between these elementary particles. Okay. So the gravitational force perhaps is the most familiar to us. Okay. So is electromagnetic. Okay. Maybe a little less familiar, but most of what we see is because of the electromagnetic force. Okay. But at the level of subnuclear physics, we also have to deal with strong forces. These are, for example, necessary for explaining how protons and neutrons bind inside a nucleus, or how quarks and gluons bind inside a proton or a neutron. Okay. There is a weak interaction which is needed for explaining various phenomena that we observe at the level of subatomic particles. Okay. And I have also added the Higgs force. Okay. Sometimes this is combined with the weak force, sometimes the Higgs force is bunched with the weak force, but this is really a different kind of force. Okay. And this arises because of the Higgs particle that you heard of in the last talk. Now, it turns out that the effect of gravitational force between elementary particles is negligible compared to the other forces. Okay. And to see this, one can simply compare the electrostatic force between two protons with the gravitational force between two protons at rest. Okay. And this can be done with just simple knowledge of high school physics. So, I will try to describe how this comes about. Okay. So, here is the result. So, the gravitational force between two protons. Okay, I have just taken protons as an example. You could replace protons by electrons. The final conclusion does not really change very much. Okay. So, the gravitational force between two protons is given by the Newton's law of gravitation. So, this is the Newton's gravitational constant, mp is the mass of the proton, and r is the distance between the two protons. And similarly, the electrostatic force between two protons is given by the Coulomb's law of electrostatic repulsion, which is given by this formula over here. Okay. And because both of them follow inverse square law, we see that the ratio is a universal constant, okay, which can be computed once you know the values of these fundamental constants. Okay. And what one finds is that this number is a dimensionless number, but it is extremely tiny, it is of the order of 10 to the minus 36. Okay. So, this is a clear demonstration that gravitational force is small compared to the electrostatic forces, and one can do a similar calculation involving other forces, and one finds that all the other forces at the level of subatomic particles are also much larger than the gravitational force. Now, this is important because it turns out that if we are willing to leave out gravity, okay, then there is a mathematically consistent theory which has been so successful that it has come to be known as the Standard Model. Again, you heard about this in the last talk. And this Standard Model describes all the elementary particles and their forces, provided we are willing to leave out gravity. Okay. And this theory is based on two of the main pillars of 20th century physics, namely quantum mechanics and special theory of relativity. Okay. However, despite its many successes, we know that the Standard Model cannot be the final story because it does not include gravity. Okay. So, gravity, as we argued, is very, very weak force at the level of subatomic particles. Nevertheless, it is very much present in the universe, and so any theory that does not explain gravity cannot be a complete story, and that is one of the reasons why we know that Standard Model cannot be the complete description of nature. So, then the first question one would like to ask is it possible to modify the Standard Model so as to include gravity? Okay. And for this, you have to recall again that the Standard Model is based on the principles of special theory of relativity and quantum mechanics. Okay. So, if we want to incorporate gravity in the same framework in which Standard Model is described, we have to first make the theory of gravity consistent with the principles of special theory of relativity and quantum mechanics. Now, the first step, which is to make gravity consistent with special theory of relativity, this in fact was carried out by Einstein in 1915, and we are now celebrating the 100 years of that discovery, and this led to what is called the general theory of relativity. Okay. So, general theory of relativity is a theory that incorporates gravity into the framework of special relativity. Okay. However, it turns out that the second step, which is combining this with quantum mechanics, turns out to be extremely difficult. Okay. Many people have tried in various different ways to make gravity consistent with quantum mechanics, and the straightforward approach always seems to run into difficulties. Okay. And this is where string theory comes in, okay, because string theory provides a possible way out of this problem. Okay. So, in the rest of the talk, I will try to describe the basic idea of string theory and then what are its difficulties and what are its successes. How much time do I have? 13 minutes. Okay. So let me begin by giving you the basic postulate of string theory. Okay. The basic postulate in fact is very simple to state. Okay. It says that the elementary constituents of matter, which we conventionally think of as particles, okay, are in fact not point particles, but one-dimensional strings. Okay. And one-dimensional strings are similar to the strings that we are familiar with in nature. Okay. For example, you have seen probably all stringy instruments. Okay. Strings are one-dimensional objects like that, but of course at a much smaller scale. Okay. And strings can of course exist in various vibrational states, that this we must again be familiar with from the musical instruments. A given string can vibrate in various harmonics and with various amplitudes. Okay. And it turns out that in the context of string theory, a string vibrating with various amplitudes and various harmonics appear to us as if they are different kinds of elementary particles. Okay. Now, why do they appear to us as elementary particles? The reason is simple. One can estimate within string theory the typical size of a string, and one finds that it is extremely small, it is of the order of 10 to the minus 33 centimeter, okay, which is much smaller than the length scale that can be probed by any present experiment. Okay. And so in comparison, I should just say that the present experiments, for example, the Large Hadron Collider that you heard of again in the last lecture, can probe a distance of order 10 to the minus 17 centimeter. Okay. So if you really want to discover the stringy structure, okay, of what we think of as elementary particles, we have a long way to go. Okay. Put another way, to a present day experimentalist, the states of the string will appear to be particle-like objects. Okay. So any possible test of string theory has to rely on indirect means. Okay. You cannot really discover the stringy structure of elementary particles just by doing direct experiment, okay, because their sizes are so small. Now, this was of course out of the blue. Okay. This, whatever I said, told you so far has nothing to do with gravity. We simply replace the notion of particles by strings. Okay. Now, because quantum mechanics and special theory of relativity have been so successful in explaining all data that we know of today, we want to formulate a theory of strings consistent with the same two principles. Okay. It should be consistent with the principles of quantum mechanics as well as special theory of relativity. And here one finds one's first surprise. It turns out that as a consequence of these two requirements, strings automatically exert gravitational force on each other. Okay. So gravity in some sense is not put in string theory. You never demanded that you need gravity, okay, but it's in a sense impossible to get rid of gravity once you have the notion that the elementary constituents of matter are strings. Okay. So string theory automatically gives a quantum theory of gravity, and this in fact is the main reason why most of us are excited about string theory. Furthermore, one finds that the requirement of mathematical consistency completely fixes the underlying laws of string theory. Okay. In other words, there is a unique string theory. Okay. Now, this is simple to state, but it took a while to discover that string theory is unique. Okay. In fact, in the early days of string theory, people believed that there are 5 different consistent string theories, okay, and that was somewhat of a puzzle, and only in the mid 1990s we came to realize that all of these 5 different are apparently 5 different string theories are in fact different ways of describing the same underlying unique theory. Okay. Now, this has to be contrasted with the theory of point particles, okay, quantum field theories that Nima talked about in the last lecture, okay, of which there are infinite number of consistent theories. Okay. Of course, quantum field theories are constraining. You cannot just write down any quantum field theory and make sense of it. Okay. Nevertheless, it turns out that there are infinite number of consistent quantum field theories that one could write down, and standard model is one of these consistent theories that is favored by experimental results. Okay. So, in this sense, string theory of course is much more unique, okay, because there is all the underlying laws are fixed. So, the uniqueness of string theory and the fact that it incorporates quantum theory of gravity makes this a strong candidate for the theory that describes the fundamental constituents of matter and their forces. Okay, because if we want a theory that describes the fundamental laws of nature, okay, it better be that there are some principles that guide us to that theory. Okay. Now, of course, this is good theoretically, but eventually we always have to face experiments. Okay. So, if you really want to confirm that string theory is the right theory of the world, it is the right theory of nature, then we need to verify that string theory also explains the origin of electromagnetic, strong, weak and Higgs forces, okay, the kind of forces that we actually find in experiments. Okay. Now, it turns out that this is not completely straightforward, okay, and this is where the main bottleneck of trying to make string theory connect to experiment lies. Okay. And the difficulty in doing this is related to what is now commonly known as a string theory landscape, okay, and I will try to describe qualitatively, okay, what this landscape means and why it gives rise to a bottleneck in making string theory, connecting string theory directly to what you observe in nature. Okay. So, this is best described by drawing an analogy. Okay. So, let us imagine that you have a particle moving in a potential, okay, just classical mechanics, okay, and let us imagine that the potential is very complicated, this has many ups and downs. Okay, I have assumed that this is a particle in one dimension, but you can easily generalize it to multi dimensions. Okay. Now, it is well known that once the potential is given, the laws of motion, okay, the classical laws of motion of the particle are completely fixed, okay, because the force acting on the particle is given by the gradient of the potential, and then once the gradient of the potential is given, the force is known, and then hence the motion of the particle is determined. Okay. Nevertheless, if you have a certain amount of energy, if the particle carries certain amount of energy, okay, and if the energy is not too high, okay, we know that the particle has a possibility of getting stuck in different wells. Okay. For example, if you have an energy which is given by, say, this horizontal line over here, the particle may be confined to move in this inside this well or inside this well or inside this well, okay, but it does not simply have sufficient energy to go from this well to this well or to this well. Okay. It is stuck at where it is kept, okay, at least in the classical physics. Okay. And the situation with our universe seems to be very similar. Okay. It turns out that string theory, okay, has a diagram, underlying diagram of this kind, although it is much more complicated, the physics is also more involved. Okay. Nevertheless, one simple way to draw an analogy would be to say that just like a particle can get stuck in these different wells, our universe may also get stuck in different phases of string theory. Okay. So, like different minima that we see here, you can think of that we call the different phases of string theory, okay, and depending on the initial conditions or various other possible data, our universe may be stuck in one of these minima or this minima or this minima or this one, okay, and this is what is called the landscape of phases of string theory. Now, it turns out that for some phases of string theory, the environment is very similar to what you observe in nature, okay, and when I say it is very similar, I mean that it has elementary particles and forces which are similar to what we see. Okay. Again, particles inside quotes, because particles are not really particles, okay, they are states of the string, but they just look like particles to us. Okay. But I should add that there are also other phases of string theory which are very different environment. Okay. In fact, they are so different that it is even hard to imagine. Okay. Even the dimension of space which we are familiar with, or 3 dimensions of space, okay, is not true in all the phases of string theory. Okay. In some of these phases, for example, the dimension can go all the way up to 10 instead of the usual 3 dimensions that we are familiar with. So, the big question of course is there a phase of string theory that describes exactly the universe in which we live? Okay. We have not yet found one, okay, because if we did find the right phase of string theory that describes exactly the universe that we live in, then we could make direct connection with what we see in experiment. Okay. All that we can say at present is that there are many phases of string theory whose properties are very similar to what we see in nature, but we have not so far found one whose property is exactly the one that we see in nature. Okay. But the search for such a phase is still on, and this is in fact one of the very active areas of research in string theory. But this is not the only area of research that string theory tries to explore. Another area of research involves using the laws of string theory to answer various puzzles that arise when we try to combine gravity and quantum mechanics. Okay. And these questions can be addressed because some of these issues are universal. It doesn't depend on which phase of string theory you live in. Okay. There are puzzles involving gravity and quantum mechanics which arise in all the phases of string theory, and so the underlying laws of string theory can be used to try to address some of those issues. Yet another area of research involves attempts to gain a better understanding of the underlying laws of string theory itself. Okay. While we have good understanding of what the underlying laws of string theory are, okay, we would like to improve our understanding. Okay. In particular, as I told you, that for a long time we thought that we have understood string theory quite well. There are 5 different string theories, and then suddenly we discovered that those 5 different string theories are in fact different ways of describing the same underlying theory. Okay. So even though we have good understanding of the laws of string theory, we don't know whether that's the best way to view string theory, and so to look for different ways of viewing string theory is one of the active areas of research. Okay. So all in all, I'll end by saying that string theory is an exciting subject, okay, and I'll finish with the hope that some of you will be participating in this adventure in the near future. Thank you very much.
Thank you, Ashoke. And so now I guess you're all in the right frame of mind. So as Nima said, just jump in, ask questions. So when you take, so I think there are mics going around. Yeah, so just put up your hand if you want to ask a question. When you ask a question, it would be nice if you just introduce yourself. I mean, say what stage you're at in your studies or something like that.
Good morning, sir. Nima sir, Ashok sir, and Rajesh sir. I'm Samip Velani. I'm in the first year MSc class in here, studying in Christ University. My question was, we say that the Higgs field is associated with giving mass to a particle. So should that have some correlation between towards gravitational field? Because gravity is also a consequence of something having mass. Is there any connection between Higgs field and gravitational field?
The answer is not a very direct one, and that's related to the fact that when it's said that the Higgs gives mass to particles, it's a rather loose way of speaking. For example, most of the mass in your body is a consequence of, it's in the protons and the neutrons, and most of the mass in protons and neutrons actually has nothing to do with the Higgs. So the Higgs is directly responsible for the masses of the really elementary particles. So the electrons and the quarks inside the protons get their mass from interacting with the Higgs. But it turns out that most of the mass of the proton actually doesn't have to do with the rest mass of the quarks that it's made of, but has to do with the energetics of the gluons that are gluing them all together into the proton. So the Higgs does play, however, I mean, it does have a huge impact on everyday life. It does give the electron a mass. If the Higgs didn't exist, the electron would be massless. There would be no atoms because there would be the electrons would be zipping around at the speed of light. Nothing would make them go around the atoms. So no. But the Higgs is very important. It gives mass to elementary particles, but it's not directly associated with gravity.
We have all studied about weak nuclear force. We know we can use it to understand different phenomena at the nano or microscopic scales, let's just say. Have we been able to quantify the weak nuclear force and give some formula to it or something like that?
Yes. Most certainly, yes. So in fact, people knew about the weak nuclear force really, indirectly they knew about it since the late 1890s. So there was in a sense, it took essentially a century to really completely understand the weak nuclear force, but it started in the late 1890s when people discovered radioactivity. Okay, and then when people understood better what was in the nucleus of the atom, we knew it was made out of protons and neutrons. The reason it's called the weak force is because you have a neutron sits there in empty space. It's this teeny tiny thing, and it takes 15 minutes for it to disintegrate into a proton, an electron, and something called an anti-electron neutrino. 15 minutes is a gargantuan timescale compared to all of the timescales associated with these teeny tiny things, so that's why there is an extremely weak force. Now, just that interaction was already parametrized well enough for most applications by Enrico Fermi already in the 1930s. But in the attempt to understand where it really comes from and what would happen if you tried to probe it at higher energies, around 100 times smaller than the nucleus of the atom, people realized that there was an essential difficulty. It was the essential difficulty I was briefly alluding to in my talk, that that ultimately needed the existence of the Higgs particle to make complete sense of it. So it wasn't until the Higgs was confirmed that we can say we really have a complete understanding of the weak nuclear force. And something maybe I'll just add quickly, with the discovery of the Higgs, something really qualitative changed in our understanding of nature. We now have a set of rules, a set of laws that can be self-consistently extrapolated to incredibly, exponentially higher energies, exponentially shorter distances than we have, than we're probing right now. Really, over the past 100 years, even longer, 400 years, we've always been in a situation where there was something right above our nose, right under our nose, that we couldn't directly explain. But now at least there isn't a burning question that immediately tells us that a factor of 3 higher in energy, something new has got to happen. What is left, however, is some burning conceptual questions, because the answers that we've gotten and what nature has handed us, while extremely simple, are extraordinarily strange in many ways, and they leave us with these very profound conceptual problems that we have to confront.
So one of the last questions.
Okay. No, maybe would you like to just add the agreement between theory and experiment for the weak force, since he was asking about how quantitative.
Oh, look, sorry, I didn't understand that part of the question very well. Just to give you an idea of perhaps the most precise prediction that's ever been made in physics is this famous prediction for the how magnetic the electron is. Okay, so the electron is a little spinning top. It has a magnetic moment, and in some units, the magnetic moment is 2.001 ... and it goes out to 12 decimal places. Well, of course, it goes out to infinitely many decimal places, but we've measured it to 12 decimal places, and theoretically, it's been predicted to 12 decimal places. Now, just so you have an idea of how well we understand the weak interactions and why and how it's important, to get the last 2 of those 12 decimal places, we need to know everything about the details of the weak interactions. Okay? So it's needed and is understood and is relevant at that level.
So my last question. We see that the LHC and all the other experiments have a particular limit to how small they can probe. Like they have only gone till 10⁻⁸, some meters or centimeters. And the actual length scales as strings exist in is 10⁻33. Is there any way that we can actually go down to that level and actually observe those, at least the effects of those phenomena, if not see them? Of course, seeing them would also include light into the picture, which might not be practical. Is there any way we can at least probe the effects of those tiny things at 10⁻33?
So first of all, of course, as you understand, but just to be clear about it, there is a difference between what the practical issue is, very important practical issue, and what the in principle conceptual issue is. There's no, in principle, conceptual problem with testing string theory. If we could build an accelerator as big as the galaxy, which we're not going to do tomorrow, or perhaps anytime soon, but if we could do it in our universe. The material is there, the stuff is there. We could, in principle, build an accelerator big enough to smash particles into each other at high enough energy and see that things are made of strings. This is not philosophy. It is physics. But it could be very, very difficult. Obviously, it is very, very difficult. So if the question is it practical to build accelerators on the planet Earth that will go up to Planckian energies, certainly not anytime soon. No kind of technology anyone can think of is going to get us there anytime soon. However, there is a couple of things that we can do, which are necessarily more indirect. So they're not necessarily going to tell us there's strings up there, but there are various things that we can do to probe for very, very high energy physics. One thing that you can do is to look for incredibly rare processes which for good reasons in understood physics shouldn't happen. And therefore, if they do happen, they're coming from some incredibly weak force, like the weak interactions we talked about before, right? The only reason people notice the weak interactions are so weak, but they made neutrons decay. There's no reason on Earth neutrons should decay, and yet it's sitting there for 15 minutes and eventually it decays. The fact that the neutrons decayed told people like Fermi that there's something going on at distances of 10 to the minus 16 centimeters. There's something going on at that scale. So we could do analogous experiments, and people have been doing analogous experiments. For example, you could look to see whether protons decay. And in our standard understanding of physics, protons don't need to decay. They shouldn't decay, but there's no deep principle that prevents them from decaying. So you can make huge vats of water, enormous vats of water, and then you just wait to see whether one of the protons in the hydrogen atoms decay. If we see something like proton decay, then we're probing scales that are close to the energy scales of string theory. So that's one way, one indirect way. Another somewhat more direct way, although still a little indirect, is to look in the sky. Look at the pattern that we see in the cosmic microwave background. So we have a very, very beautiful picture of the early universe where ultimately the entire observable universe that we see came from blowing up very, very rapidly, minuscule patch, which started off enormously small, incredibly small. That's this picture of inflation that took a tiny patch of the universe and blew it up to be the entire observable universe. It's conceivable that the size of that patch to begin with was not far from the scales of string theory. And in that case, we could look indirectly for the effects of that underlying physics. In both of these cases, we would have to be a little lucky to see it in our lifetimes or anytime soon. But, and perhaps this is something worth emphasizing to people who are thinking of getting into this business. This is something which is often compared to, the centuries that people spent building temples. You do it because you think it's important, and because you think it's deep and worthwhile. And there's no guarantee that you're going to live to see the end of it, or you're going to see the fruits of your labors. So you need to have that kind of intellectual stamina and sort of character to be able to take it. But the reward is that you're working on the deepest problems that humanity's ever thought about, and you might help take some small steps towards making sense of it.
Okay, I'm very sorry, just the last question. The LHC has been going through a lot of new developments, and we have been probing. We have been having breaks between two particular experiments. Like last time it was on is 2012. Soon it's going to get on again. So the difference is mostly the energies that we are working at. My question is, why do we have to probe for higher energies? What is the connection between going for higher energies and the properties that we are looking for?
Yeah, so the most obvious thing is that higher energies corresponds to shorter distances. So that's the basic fact about quantum mechanics and the uncertainty principle. It's sort of ironic. The LHC is probing the tiniest distances that human beings have ever looked at. and it's the hugest machine that anyone has ever built. So why do you need an enormous machine to probe tiny distances? It's because of the uncertainty principle. You need to go to these incredibly high energies in order to be able to study them. So we keep going to shorter distances. So if you stop at some energy, that's exactly the limit of the magnification that you get to look at. And so every factor of 2, you're winning a lot. If I can just say it's slightly more detail, there's a fact. It's not an obvious fact, but it turns out that the rate for producing new particles at machines like the at machines like the LHC scales roughly like the 4th to 5th power of the energy with which you collide them. Okay? So that's why it's a really big deal when you go up in energy, even by a factor of 2. You might think, oh, it's a big, what's going to happen at a factor of 2? You haven't seen something now. What is there any hope you're going to see something just by a factor of 2? Doesn't seem like a big deal. But it increases the rate at which you produce particles by almost a factor of 50. So it's a very big deal, in fact. And that's why there's a lot of excitement about what's going to happen this year and next year as it turns on again with the energy roughly 2 times bigger than what it was before. Of course, the overall reach is twice as powerful, but also it could well be that there are things that the previous version just missed because you weren't making enough of them, but you're going to make vastly more of them now.
I don't know, Ashok wants to add something about string theory and experiments.
Look, I probably.
Yeah, that's all.
Yeah, so the other way string theory could try to make connection with the experiment is what I described, that right now the reason that string theory cannot make connection is because of these many different phases of string theory. Right? But if somebody someday has a bright idea and can identify which particular phase describes us, right, then you can in principle calculate everything that you want to know. Right? For example, the masses of all the elementary particles you could calculate from first principles. Right? So that will be another way of verifying direct experimental verification of string theory, okay, although you don't see the strings themselves. Okay. But again, I mean, it's probably going to take as much time as building an accelerator of galactic size. But okay, we have to, yeah, maybe hopefully not. I mean, it depends on our mental abilities. Right?
Hello.
Yeah, so there's a question over there. Okay.
Hello, sir. I'm Santosh. I just joined the first year BS here. And this is just my thought to explain the very short distance of nuclear forces and why is gravity 10 power 42 times weaker than the nuclear forces. What if the nuclear forces decay at that infinite potential barrier and by the quantum tunneling effect decay into gravity?
No, I didn't understand the last part, which you were saying about the first part you were asking about why is the nuclear force so much stronger than gravity?
No, we know that nuclear force is about 10 power 42 times stronger than gravity.
Yes.
And it's like a very short range. So at that particular infinite potential barrier where the nuclear forces suddenly stop working, what if at that barrier by quantum tunneling effect, nuclear forces decay into gravity?
First of all, there's actually 2 things that are going on in comparing the nuclear force and the gravity. You mentioned 2 of them. The fact that the nuclear force is short range and gravity is very long range, right? So that's one difference between them. But then when you go to very short distances, you go inside the protons and neutrons, you see the quarks and the gluons, and indeed, the interaction between the quarks and the gluons are vastly stronger than the gravitational interactions. And as Ashoke was showing also, even the more familiar electric forces are vastly stronger than the gravitational ones. So absolutely, that's one of the really big mysteries. We don't understand why that's the case. At a deep level, we don't understand why it's the case. That's related to this question of why the world is big. So it's a very good question. We don't know why it's big. But so you had some thought, something about nuclear forces tunneling, decaying into gravitational forces, and so on. And those are reasonable sounding words. But as I mentioned towards the end of my talk, the biggest challenge that one has when you actually do physics is to figure out how to take words that sound reasonable and see whether they are actually reasonable and whether they make sense and whether they're compatible with everything else that we know. And what you find is that the vast majority of words that you can construct in a sentence that sound good make actually no sense when you try to fit them into the framework of physics as we understand them. So that's not to discourage coming up with words like this, because ultimately every act of trying to do something new starts with something that might sound strange or odd, but it's to encourage you to learn as much about the way physics actually works, to be able to, as quickly as possible, prove your own ideas wrong. That's the biggest challenge in physics. That's why you go to school, and then graduate school, and then a little bit more after that, and then you become good at proving things wrong as quickly as you can and trying more and more ideas. So what I'm telling you is that even ideas vaguely like that, even great people have had ideas vaguely like that, but nothing like that comes close to working.
Maybe I can just add.
Yeah.
Yeah, maybe I'll just add some things to it. So, I mean, one way to ask this question of why nuclear forces are so much stronger than gravity, you can ask us why is the proton so light, right? Because after all, why is gravity weak, right? Gravitational force is proportional. We saw is proportional to the square of the mass of the proton, right? So if the proton was very much heavier, right, then gravity would be as strong as other forces. Okay. So that is the right question to ask, and that happens to be a specific property of the phase you are living in. There are many phases of string theory that you can find where the analog of the protons would have been much heavier, okay, and there will be no distinction between the strength of gravitational interaction and strong interaction, or the version of strong interaction, some version of strong interaction. Okay. So you can pose the question in this way, that why is the phase that we are living in has this peculiar property? And that perhaps gives us a clue on what kind of phase describes us. Okay. And in the question of your tunneling, I mean, of course, the forces don't tunnel, right? But we could, in principle, tunnel from one phase to another phase. So it could happen that today we are living in a phase where all forces are not of the same strength, right? The nuclear forces are much stronger than gravitational force. But maybe we can also tunnel to another phase, okay, of string theory, where all forces will be of the same order, right? So if you want to make sense of the kind of question you're asking, maybe in that sense, you can pose this question, that is it possible that we tunnel into another phase where maybe all forces will be of the same order?
Who has the mic? Okay, go ahead.
Good afternoon. I'm Rakshit, and I'm currently doing my 11th standard now. And I came here with 3 main questions. And my first question was, where are we on the progress of dark matter and dark energy, and how they actually are going to influence the experiments we do in quantum mechanics and string theory? The second question I had was, what exactly does supersymmetry mean when we say supersymmetry? What exactly are we talking about? And my third question was that we have string theory as one of the theories that can possibly explain the universe. What are the other contending theories to string theory?
Should I start with the supplement? Yeah, we can trade around. So the status of our understanding of dark matter and dark energy, so as you know, but I'll just quickly say, we know that the stuff that we're made out of, ordinary matter, is a very small fraction, maybe 3%, 5% of all of the mass and energy that there is in the universe. Around 70% of it is in what looks more or less like an energy of the vacuum, it's sometimes called the dark energy, and the rest of it is in matter, roughly like our matter, the non-relativistic, heavy, massive particles, but which don't shine. They don't interact with light, and they interact with us so weakly that we haven't seen them yet. So the question is, what's the experimental status of these two things? Actually, the period that we're in right now, the next 5 years, are probably the close of the first major push to discover dark matter particles directly. There's a very simple picture for what the dark matter might be, which are particles, heavy particles, that don't interact with us through light, but interact with us, roughly speaking, through the same kinds of weak interactions that we've seen associated with radioactivity. And in a picture like that, the way you look for them, if these particles are out there, they would have a mass around 100 times or 1,000 times the mass of the proton. And there would be one of them, roughly speaking, one of them in every liter in this room. Okay? There's one of these dark matter particles. They're zipping through the room at 1/1000th the speed of light. So that's a fair number of them. That's quite a number of them. But they're very weakly interacting. And the way you look for them is you go deep underground in some mines or various experimental facilities deep underground. So you're shielded from cosmic rays and all sorts of other junk that's coming out from the outside. And you take huge vats of metal. You cool them down, and you just wait for one of these dark matter particles to bang into them, shake the particles to give off sound waves, give off light, and that's how you look for them. So those experiments are very mature. They're proceeding now, and they're in the middle of the most interesting part of the parameter space, where we'd expect to see at least the simplest versions of dark matter. So you should really stay tuned for that, and the next 5 years are really the sort of most crucial part for these experiments. For dark energy, people are looking at trying to measure its properties more accurately. So the best picture we have for what the dark energy is that it's just an energy of the vacuum. And if it's really an energy in the vacuum, it has the property that the energy density stays constant as the universe grows in size. Okay? So you can try to measure how the energy density varies as the universe expands. You can try to measure that accurately by accurately measuring the distances to distant galaxies and so on. And so there's a big experimental program that's looking to do that and trying to measure the amount by which this energy density might be changing. And the idea is that they're going to measure it to around the 1% level, the few percent level in the next 10 years or so. So that's the experimental status of dark matter and dark energy. You also asked about supersymmetry. What is it that we mean when we say supersymmetry? I can give you an analogy. Of course, 100 years ago, people knew about particles like protons and electrons. Well, they didn't actually quite know about them, but they knew enough to know, to strongly suspect that things like protons and electrons existed. But we were in a primitive state of our understanding of relativity and quantum mechanics. People, specifically Paul Dirac, realized that when you combine relativity and quantum mechanics, when you see, especially if you take a quantum mechanical theory and you discover that there's a new symmetry between space and time, which is what relativity tells you, that's only possible if you double the world. There have to be twice as many particles than you knew about. And those were the antiparticles of the electrons, antimatter, anti-electrons, antiprotons. Of course, no one had seen anti-electrons or antiprotons, but eventually, not too far after the prediction was made, they were actually seen in experiments. So that was an early example where an extension of a symmetry between space and time forced you to double the world, forced there to exist a ton of twice as many particles as anyone knew before. Supersymmetry is, as I mentioned, it's the last kind of thing that nature can do at long distances that we haven't yet seen it do. But the best way of thinking about it is it's an update, it's an extension of Einstein's picture of space-time that makes space-time a little bit more quantum mechanical. So ordinary space and time directions we measure with ordinary numbers, like 10 meters and 5 meters. Something is 10 meters this way and 5 meters that way. Those are ordinary numbers. They satisfy that 10 meters this way times 5 meters that way, 10 times 5 is equal to 5 times 10. They're completely ordinary standard numbers. But quantum mechanics tells us that we can have more unusual sorts of numbers show up in our description of physics. And in particular, you can have numbers that have the opposite property, that A times B is equal to negative B times A. Okay? So supersymmetry is an update of special relativity. It's an update of space-time that includes additional dimensions of space, if you like, but the distances in these additional dimensions are measured in these funny numbers that don't satisfy A times B equals B times A, but satisfy A times B equals minus B times A. And that, once again, involves a doubling of the world. So for every particle that we know, there should be an electron is moving along this way. But for every motion, allowed motion of a particle we know, there should also be an allowed motion where you take a step in this quantum dimension. And when you take a step in this quantum dimension, it looks like a particle with identical properties, except the spin is different. So that's what we'd expect to see. And that's what people are concretely looking for at the LHC. They're looking for cousins of all of the elementary particles that we've seen with a different spin, and very characteristic ways that they're produced and they decay. And so it's a very concrete set of theories that are actually being looked for by the experimentalists. And I'll give it to Ashoke for the third question.
What was the third question?
About different approaches.
My third question was that...
Yeah, maybe before I do that, I'll say a few words about the dark energy. Okay, and probably I can just go back to the... I'll just show the figure, since the figure is already there, so I can... Yeah, so this I showed this figure as different phases of string theory. Okay. And so in this figure, if you want to know what dark energy corresponds to in this figure, it's basically the height of the minimum. Okay. So this particular phase would have no dark energy. Okay. This one will have some dark energy, this one will have even more dark energy, and so on. Okay. So this is the way dark energy can possibly arise in string theory. So the puzzle is not that how we have dark energy, but what one finds in string theory, and in fact in any attempts to incorporate dark energy, is that the typical values of these heights, okay, is 10 to the 120 times more than what we see in experiment. Okay, so the question not really is how to explain dark energy, but why is the dark energy so small? Okay, the dark energy that we see in the present universe. And this goes back to the same question that Nima raised, that why is the universe so big? Okay, if the dark energy was really 10 to the 120 times bigger, our universe will be that much smaller. Okay, so this is what I can say about dark energy. Okay, now about the alternative theories. Okay, I think besides string theory, there is another possible attempt to quantize gravity, which is called loop quantum gravity. And I may be biased because, of course, I work in string theory, but my general view is that loop quantum gravity hasn't really gone anywhere as close to string theory in trying to incorporate gravity and quantum mechanics together. And one of the reasons I believe that that is the case is because if you work with loop quantum gravity, you cannot, for example, find an explanation of why do we have classical gravitational laws between ordinary bodies at large distances. Okay? So loop quantum gravity is a formal way of trying to quantize gravity. But starting from there, you cannot go to the classical limit where you see the normal gravitational force, classical gravitational force. Okay. So in that sense, I would say that string theory is much more ahead than its contenders in terms of quantizing gravity.
Can I add a comment to that? So one more comment along those lines, because it's related to what I was mentioning in the talk. We have this, so we have as Ashoke beautifully reviewed, we have problems trying to make sense of what gravity looks like at very high energies. But we're in this big straitjacket of trying to be consistent with these laws that we know already of relativity and quantum mechanics. So that means that even though the experiments can be very remote, even though it can be very difficult to go to the Planck scale, all those things that we talked about, if you can find, it's still possible to at least try to make some kind of progress by trying to find at least one example of a theory that's compatible with these basic principles, and that which you can check. Now, that's what's so exciting about string theory. In the 50 years that people have been trying to do this, there are very concrete physical questions that you can ask. You know, if you collide two gravitons together, two gravitons go in, two gravitons go out. there's a very obvious physical question. You want to know what is the rate at which that happens? What is the, what's the probability amplitude? If two of them are coming in this way, that they go out at 40 degrees relative to the angle that they came in at. There's a concrete mathematical formula. There's a concrete answer in nature. We don't know what it is because we haven't done the experiment. But if there's an underlying theory, there's a concrete mathematical formula that answers that question. And that formula needs to be compatible with relativity, and it needs to give you, make sure that the probabilities are well defined and they add up to 1. Okay? So there's a way you can begin, which is to try to find one example of a formula like that. Now, maybe there's 15 million examples, and then we'd have to use experiment to decide which one is right. But you can begin by just trying to find one. And this is why you need to go to school and study and things like that to appreciate the statement I'm about to make. But it's amazingly difficult to come up with even one such formula. In fact, when you first look at the problem, you think it's incredibly simple. You think any sort of dumb modification of the normal laws would make it work. And then you study in detail, and always one of the two things bangs you over the head. It's either not compatible with relativity or not compatible with quantum mechanics. So there are these miraculous formulas that are actually compatible with relativity and quantum mechanics that, in fact, were discovered first, and later people realized that there was a picture that things were strings behind them. That's a big reason people are so excited by it, because for the 50 years that people have been thinking about this problem, there's essentially one set of formulas that make any sense. And there's much, much more to string theory than that. But that shows how A, how non-trivial it is, and B, how it's possible to make some progress purely theoretically. Now maybe one of you or someone will discover another formula. And it's not a matter of sociology. It's not a matter of there's this club, there's another club, some people something is pretty, other people don't think something is pretty. You know, a complete unknown person out of left field, if they come out with another formula, it'll be incredible. People will have to pay attention and look at it. So it's not a matter of aesthetics, that there are some real, actual, concrete physical accomplishments, which doesn't mean that it has to be the theory that describes our world, but it's passing such incredibly tight requirements that it's impossible to ignore.
Good afternoon, Professor. I'm Anup, and I'm in my first year undergraduate. I have two questions. The first one is about Einstein's cosmological constant. Is the concept of Einstein's cosmological constant consistent with the modern string theory approach? And my second question is about the many worlds interpretation. Do you really believe that there are many versions of you and me simultaneously coexisting in, say, multiverse concepts?
So Einstein's vision of the cosmological constant, I mean, mathematically, absolutely. He said that you can add this constant to his equations, and that's the constant that makes the universe expand. So that's the dark energy. Now, it's a little bit ironic that Einstein added this constant to do exactly the opposite, that he wanted to use it to prevent the universe from expanding. So, in fact, in his picture, you see this cosmological constant wants to make the universe blow up. And matter wants to make it slow down. So Einstein put it in to balance matter against this thing that makes it want to blow up to get a static universe. But people, including himself, very quickly realized it was an extremely unstable solution. In fact, the universe just wants to expand, okay, or contract in Einstein's picture. So while indeed it's exactly the term in his equations that he wrote down is what we're talking about as dark energy now, even though it was very far from his intention. As to your second question, you mentioned two things. You said many worlds and the multiverse, and these are two distinct ideas. I don't know if you meant to invoke them both together. There's many worlds that sometimes people talk about in the context of quantum mechanics, that there's that when experiments are done, the universe splits into pieces, and there's many worlds, and there's a many worlds interpretation of quantum mechanics. There's that, and then there's the idea of the multiverse. They're in principle distinct things. About the many worlds interpretation of quantum mechanics, I will only say that I think, and I think many of us think that there's not very much there's not very much substance in the debate about interpretations of quantum mechanics. if you just think carefully about what quantum mechanics tells you and how you're supposed to think about quantum mechanics and how are you supposed to make predictions with it, that there's nothing mysterious or strange about any process. Everything can in principle be explained in the standard laws of quantum mechanics until we run into questions involving gravity and cosmology and the sort of deep mysteries that we're talking about. But there's nothing fancy going on with ordinary measurement processes. And in particular, this idea of the many worlds interpretation of quantum mechanics is I mean, in some that there's nothing particularly wrong with it, but there's nothing particularly useful about it either. At least that's my own view. The question of the multiverse is different, and I think there's a question that is really at the frontiers of our understanding right now. There is some sense in which that picture that Ashoke drew, there's some sense in which we're supposed to think about different regions we have what looks like a quite smooth, homogeneous universe out to distances of maybe 10 or 15 billion light years. But there's a sense in which if you take the most straightforward interpretation of Einstein's equations together with pictures of potentials like that you might imagine if you zoomed way, 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 way out, that you see an incredibly inhomogeneous universe. And in different regions, there are 15 billion light years that look like they're in the left vacuum, and another 100 billion light years that look like they're in the right vacuum, and so on. And that's certainly what happens if you take the most straightforward interpretation of the equations. And that's what makes people take the idea that there might be a multiverse like this seriously, because it comes out of simple equations that in many other circumstances we trust and we get correct predictions from. But on the other hand, it's also suspicious that all of these places in the multiverse are realized in a region that we can't get information from, in regions that light from them can't reach us, even in principle. So that's a reason to suspect there might be something misleading about this way of thinking about them all out there, somehow simultaneously and populated. And so the actual answer is we don't know. We don't know the right way of thinking about this yet. This is, I think many of us think that trying to make sense of this question is probably the thorniest conceptual puzzle that we're dealing with in physics today.
Hello. I'm Shankar. I'm in the second year.
Where are you? Oh, there you are.
BSc in Christ. And I don't know if you remember, we met yesterday at IISc.
You're very far away, so I can't.
I have a couple of questions. Firstly, since string theory is supposed to give us almost pretty much complete understanding of the universe around us, and also that you mentioned that we already know all the allowed particles in the universe, isn't it possible to sort of construct a picture of dark matter by ourselves? And why is it so mysterious that people aren't able to figure it out? And also, why is you mentioned that space-time is doomed and we need something to replace it. So if you could elaborate on that also a little bit. Yeah.
First, maybe do you want to say about string theory and dark matter?
Yeah. So first of all, I should add that it's not that we know all the particles in our universe. We know particles of mass below a certain value, right? Because any experiment you only can produce and detect particles carrying masses up to certain value. So you have no idea what happens when you go above that energy scale. Okay, there can be hundreds of particles, elementary particles, that you may discover as you go up in energy. Okay. So this is one limitation that at any given time we only know a limited amount of information about our universe. Okay, and at present that is not sufficient to identify where we are in this landscape, okay, and which particular vacuum describes us. And as I said, that's one of the challenging problems. Many people are working on it, but whether we will find a solution very soon is not completely clear. And what was the other question?
About space-time being doomed.
Okay, yeah,
I think maybe
okay.
he wanted you to elaborate on that.
Yeah. There are these very, very simple thought experiments that you can do, where you imagine looking at smaller and smaller regions of space, If you want to look at tiny regions of space, you need more and more energy to look at it. That's the uncertainty principle again. And at some point, you put so much energy into such a tiny region of space that you collapse it into a black hole. So you're trying to learn about what's going on in there, but you can't because you made a black hole. And if you get frustrated and you try to use an even higher energy experiment to see what's going on, you make an even larger black hole. So that tells you that there's no operational way of talking about distances and times that get comparable to this very, very tiny length scale, this famous Planck length scale, where gravity really becomes strong and the fluctuations of space-time become large. So that's in a sense perhaps the most fundamental aspect of this problem of a quantum gravity. There are other aspects, but that's one of the most urgent ones, and it's one that string theory, in the way, especially in its first incarnation, went down the road to begin to address, but in its early incarnation from the 1980s to the 1990s, it didn't quite address the questions of what happened at precisely this length scale, this 10 to the minus 33 centimeter length scale. Now, all the developments that Ashoke alluded to that took place after that, in principle, give us ways of understanding the answer even to that question. But while there are some in principle answers to them, they're sort of implicit enough, and we don't understand how they work enough, that it's a very active topic of research to try to figure out precisely how we make sense. You see, if space-time doesn't really exist, if we can't really measure it, there has to be some way of talking about all the phenomenon that we talk about. The seeming fact that we're sitting around in this room and talking to each other and all of these things are fundamentally approximate. The concepts of you being there and me being here, the position in space-time you're at, the position in space-time I'm at, these are not things that will occur in the correct theory of the world. The correct theory doesn't have those ideas. It has some more primitive things, out of which these things are approximations. And we don't have a complete understanding for what those more primitive ideas are. String theory has gone a fair way, but certainly not all the way to at least making it possible to more concretely tackle these questions.
Yeah, I can just add one more thing that, I mean, in string theory, as Nima mentioned, the things to do with black holes are still not completely understood. But within string theory, one can construct explicit examples where you start from two different manifolds which are topologically distinct. Okay? And you know that by the usual concept of geometry and topology, you cannot continuously change one topology to another topology. Okay? The simplest example is a sphere and the surface of a tire. You cannot deform continuously a sphere to the surface of a tire. Okay? But one can construct explicit examples in string theory in which two topologically distinct manifolds can be continuously deformed to each other. Okay? And the way it happens is that it goes via a configuration where the geometry, idea of geometry breaks down. Okay? So here is a clear example why, I mean, where you see that the usual notion of geometry and topology doesn't work in string theory. Okay? Now, we still don't have a complete understanding or a complete picture of how this happens in general, but there are certainly concrete examples of this kind.
Just one last question. I've read a little bit here and there about entanglement and how people aren't really able to explain it. So what does string theory have to say about that?
Well, it's not that entanglement is not explainable. Entanglement is a concept in quantum mechanics, right? And I mean, there are well-defined notions and measures of what the degree of entanglement is between two different regions, for example, or two different parts of the quantum system. Okay? What string theory is attempting to do is to try to make connection between entanglement and geometry. Okay? And I should add that that connection is still not completely clear, but it seems, I mean, what emerges from this analysis, or what is emerging from this analysis, is that there is a very close connection between entanglement and geometry. Okay? If two different subsystems of a quantum system are entangled, then they also have some kind of geometric connection. Okay? But this is still in the process of development, so I don't think you should take it seriously, but it's just some thoughts you may keep in mind.
just add one thing. You mentioned that sometimes entanglement is talked about as something mysterious. That quantum mechanics is almost 100 years old. Not quite, but we've had these ideas for almost 90 years maybe. It took a while for people to understand really what was special and fundamentally different about quantum mechanics. I mean, of course, one thing was obvious right away, that quantum mechanics didn't allow you to make deterministic predictions for what happens next when you do an experiment, while classical mechanics does. But that still left open the possibility that maybe that kind of uncertainty was analogous to the uncertainty, you know, when we roll dice, or there are things that we just can't keep track of, variables that we don't know. It took a little while, not that long, but people figured out that no, quantum mechanics was fundamentally different than that. It really introduced an essentially different kind of uncertainty than people were familiar with. Far from being a mysterious thing, quantum entanglement is the engine of what makes quantum mechanics so special, and what gives rise to a host of the most important quantum phenomena. When people talk about entanglement as being mysterious still today, there's a lot of fuss made about this. People like to say that we still don't understand quantum mechanics. It's very mysterious and strange, and it is mysterious and strange from the point of view of classical physics. But it is not mysterious and strange from the point of view of the correct theory of the world, which is quantum mechanics. And our job is to figure out, is not to enslave the theory to our poor, you know, bodies and minds that have been evolved to understand what looks like a classical world. Our job is to understand nature on its own terms. And once you learn quantum mechanics and you learn the laws of quantum mechanics, they're simple and beautiful, and there's not a damn thing mysterious about entanglement. It's in fact a spectacular, beautiful, and crystal clear thing. So I encourage you to be skeptical about people who go on and on about the philosophically strange things about entanglement and non-locality and all this stuff. It's all confusions that arise when you force yourself to attempt to describe the world in a classical language when it just doesn't want to be described that way. And that's one of the most profound things that these amazing people 90 years ago taught us. It's an important lesson to keep in mind.
Thank you so much.
Good afternoon. First of all, before getting into the questions, I really need to thank you all for coming over here, because most of us we are big fans. Since the day we saw the poster up with the university, we were like, oh yes, that Saturday is going to be next door here. Some of us have had classes to come over here, so thank you so much. Okay, questions, two questions. First one is about Higgs boson. All of us have to agree on the fact that we all have heard of Higgs boson, but how much do we know about it? Okay, it's been discovered in 2012 and it's been 3 years, and yeah, it has spin zero, it gives mass, but what more has it offered to us? What's so big deal about Higgs boson? All right, and second question is string theory. String theory has inspired me a lot. I was in 12th standard when I saw Brian Greene's NOVA series of string theory, and I was like, wow. And with that mentality, I attended some talks and I've asked questions about string theory, and people gave this skeptic answer saying that string theory is it, I don't want to talk about it, but you know, they have a wrong notion about string theory. So I want you to tell me something super about string theory that I could tell those people, hey, you know what, string theory is awesome, so here it is. So,
For one thing, it's super string theory. Built into the name, you don't have to, there's nothing to do. Maybe I'll just say something about the Higgs.
Higgs,
and
yeah.
you can talk about why string theory is so awesome. The big deal about the Higgs, well, I mean, even what you said doesn't sound like such a small deal. It gives mass, you know, those sound pretty important to me. You have pretty high standards, I guess. You know, it will not solve world hunger or, you know, bring peace between Israel and Palestine and stuff like that. But it's pretty important. As I mentioned before, even that way of talking is a little bit loose when we say it gives mass to particles. It does give mass to elementary particles like the electron. It's responsible for your existence, therefore, because if the electron didn't have a mass, there would be no atoms. The electron would be moving at the speed of light and be trapped around the atomic nucleus. So you can thank the Higgs boson for your very existence. I hope that's good enough. You know, that's.
What are we going to learn about
but in fact, but more than that, I mean, that's why it's important to the universe. But why is it? But the more important question is, why is it important to the theoretical physicists, right? So, and the reason is that it's incredibly simple, but it's incredibly strange. The fact that we've never seen a particle like it ever before. As I mentioned, you know, we've never seen an elementary spin zero particle before, and so it's wonderful that we've finally seen one, but in fact, all this time that we hadn't seen one, there were a lot of theoretical physicists that thought there was a very good reason we hadn't seen one. And there were very good reasons that such particles shouldn't exist. Or if they exist, they should be at such incredibly heavy masses that we shouldn't have access to them. The fact that it exists and we have access to it actually opens up a host of very important theoretical puzzles that are perhaps closely related to the question of why the universe is big. Okay? So that's a major puzzle for a theoretical physicist. And along the way, while we're puzzling over that, our experimental friends are going to really look to see what's strange about the Higgs. I mean, we've seen all kinds of particles that have spin zero. The hydrogen atom, in one of its in its ground state, looks from very far away like a spin zero particle. But it's not elementary. It's composite. You know, you go, you see, it's made out of stuff. It wouldn't be surprising if the Higgs was composite. Odd, what's so strange and mysterious about it is it looks elementary so far, but the LHC is giving a sort of, if you think in the analogy of a microscope, is giving a sort of roughly 5 times magnification picture of the Higgs. And what you need is 100 times magnification picture of the Higgs. And that's what, well, both the LHC as well as future experiments along the lines of the colliders that I was mentioning to you, the next generation things after the LHC are really all going to be all about measuring its properties in as much detail as we can in order to see, is it really point-like? Is it really as surprising as it now seems? And so that's going to search for the answers to these questions.
Okay, maybe I'll also add something about the Higgs. I mean, for me, I think one of the most exciting aspect of the Higgs is that its existence was predicted 50 years before it was discovered. Okay, and for these 50 years, many people tried to build models without Higgs, okay, and they always failed. I mean, the standard model, I mean, I describe standard model as a theory which is well accepted, but it was well accepted before the discovery of Higgs, and people well knew that without the Higgs, it's impossible to have a theory like standard model. Okay, so this, in a sense, explains the power of theoretical reasoning. Okay, the existence of the Higgs was predicted purely based on theoretical reasoning, and we knew that even though we have never seen a particle like Higgs, it's impossible to construct a theory like the standard model without the Higgs. Okay. And I would say in string theory is we are following essentially the same spirit. Okay, we know that we have a theory of gravity. We have gravity. Gravity is an experimentally observed force. Okay, and it seems at present that it's impossible to construct a quantum theory of gravity without invoking string theory. Okay? And that, in my mind, is the most important reason why we do string theory. Okay? That if somebody tomorrow comes with a better theory of gravity or an alternative theory of gravity which is equally successful, which satisfies all the consistency conditions, we'll take it equally seriously. Okay? Now, besides gravity, as I described, that it is in principle possible that string theory could incorporate these other forces as well. But we don't know it at present. We only know that it has the possibility of incorporating the other forces. Okay? And that's one of the big challenges of string theory. And everybody accepts that that's a big challenge. And everybody is ready to face the challenge, people who are doing string theory. So I don't know, I don't think I have anything better to say about string theory than this, but it's just this. Okay, thank you.
Actually, one more thing. Just want to add one more thing, which is that when string theory first really rose to prominence in the mid-1980s, there were still sort of camps within theoretical physics. There were people who still thought they wanted to further explore what just the interactions of particles could do, or study quantum field theory. And string theory seemed different than that. It was completely removed from it. So there seemed to be disparate camps, and people fought with each other. There were arguments and debates, but string theorists themselves, and it was the string theorists who realized this, not the other guys. It was the string theorists themselves following exactly the path Ashoke was mentioning in this talk, continuing to explore the theoretical structure and the underlying laws, learning more about it. It's really something that's being discovered. It's not being invented. It's something that obviously exists out there already that human beings are learning more and more about. It's string theorists who discovered that string theory is in fact very closely related. In fact, in some sense, a different description of ordinary interactions of particles. And so quantum field theory and string theory are much, much more closely related to each other than all the peoples in these camps realized when the subject started. So that today there's not camps anymore. Today everyone realizes there's one enormous, beautiful, rich, amazing structure that has something to do with incorporating gravity, relativity, and quantum mechanics. And that everyone has been seeing different aspects of this big beast for a long time. But it's completely obvious that we're not going to get the complete picture of what it is without incorporating all the wisdom that string theory has given over the past number of decades on the subject. So that's the last thing I would say, is that it's unified everything. It's unified, not just the particles and forces, the things that you thought was going to unify. It opened up amazing, completely unsuspected connections to completely established standard parts of physics, so that it's very hard to imagine that it's going to be divorced from reality, given its close connections to things that we already know are real.
I mean, just also to add to just that theme, almost any good idea in theoretical physics has eventually been somehow absorbed into string theory, or string theory has very naturally sort of brought it out. So in that sense, that's the fundamental reason why these sort of unification of camps or areas has happened.
Sir, I'm Shotik, master student at physics at IIT Madras. I have 3 questions. First is the energy of the vacuum the only constituent of dark energy? Second is there any known experimental setup in Earth to measure this vacuum energy currently, or is it been planned? And third is for this spin 3/2 particle that is expected to be predicted in future. So how will it be different from the kind of particles we see or we are familiar with?
Maybe I'll say a little bit. The first question is how do we measure vacuum energy? Was that right? Was that the question?
That was the second one. I think the first one was, are there any other consequences?
No, first one was, is the vacuum energy the only constituent for the dark energy?
Oh, yes, sorry, yes, yeah. Was it the only well, that's an experimental question, and at the moment we don't know. But what we know is that what it means operationally for the dark energy to just be vacuum energy is that the energy density in the vacuum doesn't change with time. The density of the dark energy does not change with time. Okay? So what you can look for experimentally is to see whether there's evidence that the amount of dark energy is varying with time. Is it varying with time? What we know currently experimentally is that it's constant and it only varies by around, and this is due to the experimental error, by around 10%. Okay? So in other words, if we look now in the universe and we look when the universe was 10 times younger, the amount of dark energy has not changed by more than 10%. What the next generation of experiments is going to do is to take that 10% and change it to 1%. So if there is variation, at the, let's say, 3% level, then by the next round of experiments, we will know it. But given that it's so close to being a constant right now, and for other reasons that's harder to explain quickly in an answer, but from a theoretical point of view, it's extremely difficult to understand how it could be varying and varying just that little. I think most people's going assumption is that the dark energy is a vacuum energy. But again, it's an experimental question, and we will know more about it experimentally in the coming years. Well, the second question is, can we measure the vacuum energy like here? Right here. The main difficulty is that in the absence of gravity, vacuum energy doesn't mean anything. You know, this is what we learn in high schools, that we can put the zero of the potential energy anywhere we want. So when we solve mechanics problems, we put them in the most convenient spot in order to make our equations shorter. But it's gravity which changes that. It's because everything, energy, you know, equals mc squared, everything gravitates, and the vacuum energy curves space-time. But the amount of curvature is minuscule. The amount of curvature is of order the sort of 10 billion, the scale of 10 billion light years. That's why it's extremely difficult in any lab experiment. So what a lab experiment would have to do is, in the lab, see the slow stretching apart of space, you know, doubling in size every 10 billion years. That's why it's extremely hard to do it in the lab. The reason we actually managed to do it in the universe is that we have these signposts out there. We have these things like supernova that are very far away. And and they're very old. Their light from us come from very long distances. And so that's how we managed to do it. But it's very hard to look for it directly in the lab. What was the third question?
Spin 3/2 particle, how is it different from?
Oh, the spin 3/2 particle is, again, we've never seen an elementary spin 3/2 particle before. And so I told you that there's only a few ways you could have interacting particles. If there is a spin 3/2 particle, it would have to have the funny property that, let's say you had so you know you have an electron, and it can interact with the spin 2 particle, the graviton, and give you another electron. This spin 3/2 particle can only exist if there's supersymmetry. It can only exist if they're partners to all the ordinary particles. And the strength of its interactions are completely determined by the gravitational, by gravity. So if we have an interaction between an electron, and a graviton whose strength is gravitational, then we have to have an interaction between the electron, the partner of the electron, the superpartner of the electron, and this spin 3/2 particle, which is, in a sense, the partner of the graviton. So this spin 3/2 particle is called the gravitino, and it's the supersymmetric partner of the graviton. And if it exists, we know all of its properties. If only we find it, we know all of its salient properties ahead of time.
Is there really a grand unified theory of everything, or are we chasing examples?
Okay, it depends on what one means by a grand unified theory. I think what you are looking for here is not necessarily something that unifies all the forces, but a single theory that can incorporate all forces. Right? You cannot have, for example, a theory of gravity. Okay, on the one hand, which is Einstein's general relativity is a perfectly good theory of gravity, but it doesn't incorporate quantum mechanics. Okay. On the other hand, standard model, okay, is a quantum mechanical theory, but it doesn't incorporate gravity. Now, you could ask, is it possible to live with the two separate theories? Okay. And we know that it's not possible to live with two separate theories because, after all, electron is quantum. Right? You cannot measure the position and the momentum of the electron to arbitrary accuracy. On the other hand, electron also produces gravitational field. So if the electron is quantum, if you cannot measure the position and momentum of the electron to arbitrary accuracy, how can you measure the gravitational field of the electron to arbitrary accuracy? Right? Because if you could reconstruct the position and momentum of the electron. Okay? So this shows that it is not even internally consistent to have a classical theory of gravity and a quantum theory of everything else. Okay? And what we mean by looking for a unified theory is not necessarily something which unifies gravity with everything else, but a theory which is quantum and which can explain gravity as well as everything else. Right? Gravity may still appear as a distinct force, just like strong, weak, and electromagnetic forces are distinct forces of nature. Okay? So that has to be there. Right? Whether there is a more unified version is something that has to be answered later. But the minimal requirement is to have one single consistent theory.
Can I add something to this? That over the history of physics, really since it began, we've been making amazingly steady progress. But it's also true that the nature of what the answers ended up looking like at essentially every step. There were things that seemed very surprising, not just about what the actual physics ended up looking like, but even what the nature of the answer ended up looking like. So what people thought of as the great dream, you know, so this analog of what's the greatest dream, what's the most amazing thing we could imagine, in the 1850s, that great dream was Laplace's dream, that we will, if you give me the position and velocity of every particle, then I will predict everything about the world after that, right? That was the purpose of physics, was to ultimately predict every single thing about the world. Then we learned about quantum mechanics, and we know that that dream is wrong. It's not, so you could say, we failed, that dream has failed, you know, no one has found the deterministic theory of everything. Well, that's life, that's not what the universe is like. I think, but far from this being a disappointment, what happens all the time is you realize that, when you formulate what you think of as these sort of grand, very long-term questions, until you're kind of close to knowing what the right answers are, it's hard to ask the right question. And so the nature of the question keeps changing as we learn more about the way the world works. And so far, even when the nature of the answer ended up being very radically different than what people dreamed it would be, it's always been better. It's always been more striking, more unified, more all-encompassing than people realized before. So for instance, while it's true that the world isn't deterministic, and that may have disappointed Laplace, and in fact it did, it was a tremendous disappointment to people like Lorentz and all the old classical physicists who you know, just couldn't tolerate the new quantum picture of the world. It's exactly the undeterminism of quantum mechanics that allows this tremendous unification to take place between waves and particles. Okay? The more we understand, in much more surprising ways than people realized to begin with, we discover deeper simplicity and deeper unification. So I think the analog of that that's going on today, in the spirit of your question, is, you know, in the 1970s and 80s, people had this sort of cookie-cutter picture that we're going to have the strong force and the weak force, electromagnetism and gravity, and they fit together like a jigsaw puzzle in some super theory. And that maybe that's the way string theory would give us the answer. And that may still turn out to be that way, although I think the evidence is that there's probably something like this landscape. And often this landscape is talked about as, oh, look, that program of unification failed spectacularly. Look, you can get to the bazillion different possibilities. But it's exactly the other way around. Precisely the other way around. String theory is so unified, so amazingly unified, that it can take all of these seemingly radically different possibilities and see all of them as realized in one theory, and seamlessly connected to each other. Okay? So in my view, I think this is very analogous to the dream of Laplace turning into the reality of quantum mechanics. The dream of grand unification could turn into this kind of reality, which unfortunately we still don't understand. But you know, it took a long time for people to understand quantum mechanics. And we need to be prepared to accept that the nature of the question is very different, and the nature of the definition of progress even can be very different than people anticipated to begin with.
Yeah. I'm sorry this could go on. I'm sure many of you have questions, but in the interest of time, we have the public lecture starting at 2 o'clock, so I'm afraid we have to sort of close the session now. But before we do that, I think there are a couple of mementos from the ICTS for the speakers who've sort of so generously given their time and interacted with you. So I think, sorry, no more questions. We'll have, we'll have the public lectures, and there again, there'll be a chance to ask questions. So let me thank Nima and Ashoke again for for their patience and for answering everything. There's one last announcement. The students are requested to, all the participants are requested to collect their food coupons from the registration desk outside the auditorium for lunch. So all of you are welcome, and please come back again at 2 o'clock for 3 wonderful lectures.
Go on, guys.
Great.
That was fun.
Yeah, I think there were no